In this video, we're going to consider stress concentrations. We're going to look at this problem right here. And it says determine the maximum normal stress developed in the bar when it is subject to a tension of 8,000 newtons. We'll take a look at this. And we'll have to consider a couple of stress concentrations. There's a fillet here, and there's a hole here. So we'll do them one at a time. So first, we'll consider the fillet, which is this over here. And we'll have to keep in mind the values that we're going to need when we use our table to find stress concentrations. So first of all, if we look at the chart for the fillet, which is over here, we're going to need the width of this small part, which is H. We're going to need the large width in which this connects to. And we're going to need the thickness. And we're going to need the fillet radius. So let's write those down. So again, from the chart, this thickness here is going to be our H. And the fillet radius . 0.015 meters. And then the thickness T is going to be 0.005 meters. And finally, so again, this H is the width of this part. Then it goes into this larger part here, which is 60 millimeters. So, and that's what the chart is called W. And let's see. And then we're going to have to calculate W over H to use the chart. And we're going to need to calculate R over H. So we need those two. So W over H is going to be 0.06 divided by 0.03 for H. And that's going to be 2. And then we're going to need R over H. And R was 0.015. And H was 0.03. And we calculate those, that's 0.5. So if we look at our table here, so we have a R over H of 0.5, and then we want to see where this intersects the curve of W over H equal 2. And let's see, that looks like that curve is about right there. So 0.5 for R over H. And then it looks like it intersects W over H of 2 right there. So it looks like K is going to be about 1.4. Again, we got that from the table or the chart. And then you could calculate the stress is now going to be the stress concentration times the area of this face right here. But actually, that's given to you in the diagram here, it's P over H times T. So the stress for the fillet is going to be P. And let me make some room here because we're going to need the K in front. P over H times T. Be 1.4. And our P was 8,000 newtons. Our H was 0.03, and our thickness was 0.005. So again, the chart just told us that the stress was P over HT, but that stress concentration is multiplied there because that's always going to increase the stress value. So when we calculate this, if you put that in your calculator, you get something around 50, excuse me, not 53. You get 74.67, 10 to the 6th Newton meter squared. Then finally, so that's for the fillet. Now we have to check the stress in the region of this hole. And once again, we'll have to look at the chart, see what information we need. So for that, we're going to need the radius of the hole, the width of that region around the hole, and the thickness. So for the hole, again, we're going to need the radius of the hole. Now we're given the diameter, but so the radius is going to be 0.012 meters divided by 2, which is 0.006 meters. That's the radius of the hole. And then the width of this region here is going to be 0.06 meters. And then the thickness of the part is 0.005 meters. And then when we use the chart here, we're going to need 2R over W. So we'll calculate that. And that's going to be 0.2. And then we'll use the 2R over W to find our stress concentration for the area of the hole. And again, we said that the 2R over W is 0.2. And then read up here to this curve. Looks like that's about 2.45. And then, so the stress. And they give us a little formula here for the stress P over W minus 2R times T. Once again, we want to multiply by our stress concentration K. It's P over W minus 2R times T. 2.45 times 8,000. Our width is 0.06 minus 2 times R, 0.006 and 0.005, like this. And put that all in your calculator. That's going to be 81.67 times 10 to the 6. That's going to be Newton meters squared. Now, if you look at these two stresses that we found, this is the higher one. So that's going to be the one that determines the maximum stress. That's the higher of the two. So that's the maximum stress in our part.